for going after all the professionals and their amazing presentations, but here we go. Um, so, um, a society grows great when old men plant trees whose shade they know they shall never sit in. Today, we sit at the dawn of space exploration, able to see the possibilities ahead of us, but not having the means to explore them. The gold standard of rocketry today is chemical propellants, and we already sit at the cusp of mastery for it. We can reuse single stage rocket or first stage of two-stage rockets, and we're working on reusing the second stage. However, such mastery will not be enough for interstellar travel. What we need is not to make a longer lasting candle. We need the revolution of a light bulb. We need to plant a tree. And there are two main issues that pertain to space exploration, propulsion systems and shielding mechanisms. For the sake of today, I'll be focusing on the former and keeping it pretty basic. So using the classical Tsiolkovsky rocket equation, we can see that the fuel to payload ratio required for chemical rockets to achieve escape velocity is about a 10 to 1 ratio, which is quite inefficient. If we increase the fuel and bring the ratio to 10,000 to 1, we could only increase the max velocity by around 4 times. In fact, if we assume that we could refine every drop of oil on Earth and use it, roughly 167.3 trillion kilograms as fuel, we would only have reach a max velocity of just under 0.3% the speed of light, just propelling the Saturn V's rocket payload. At that speed, it would take over 10,000 years to reach the nearest star system. Very, very impractical. So here's 3 directions I'll talk about for today that we can work towards for a revolution. Number 1, the Orion drive, which simply put is using bombs and explosions for propulsion. Number 2, plasma propulsion or fusion propulsion. I know these two are very different, but there exists some overlap, and for today's sake, I'll just keep them together. And number 3, the solar sail, basically catching tiny photons and using their momentum to accelerate. I'll be okay. Also, I'm still researching other options, so I'll be glad to receive any input. For the sake of establishing the efficiency of each propulsion system, I will be using the fuel by mass required to achieve escape velocity as a baseline. Now, to achieve escape velocity, we've established that classic chemical propellants need 90% of the vehicle by mass to be fuel. That means such rockets only have 10% mass for literally everything else. Two-stage rockets do slightly better, but still are far from interstellar capabilities. And although my view may be a little bit pessimistic, I believe that chemical rockets have already achieved most of their potential. However, the Orion drive, based on previously mentioned calculations, only requires between 30 to 45% fuel by mass, depending on whether you want to use optimistic or pessimistic estimates of exhaust velocity, of course, assuming the use of fission bombs. Fusion bombs could provide even higher exhaust velocity and thereby less fuel by mass, which displays the existence of significant room for evolution. Of course, there's also antimatter bombs, but I won't get into that. Already, this is much better than chemical rockets. Additionally, a solid argument for this propulsion system is that it's one of the more tested propulsion systems, with many trials conducted in the 50s and 60s. If the stigma around nuclear fission is to be lifted, the Orion drive could become a viable solution. Of course, the setbacks for this propulsion system are clear: the need for a heavy and durable bumper plate to transfer the energy within the explosions to physical movement, and international laws prohibiting the use of nuclear weaponry that prevent this from existing. Theoretical top speed for this propulsion system is roughly 10% the speed of light, meaning that the interstellar travel journey would fit within a human lifespan of around 42 years. Next is plasma propulsion and fusion propulsion. There are many types of said propulsion systems, including but not limited to moderate plasma propulsion, such as variable specific impulse magnetoplasma rocket, also known as VASIMR, and advanced fusion propulsion, such as inertial confinement fusion, also known as ICF. But generally, the fuel by mass to achieve escape velocity can take anywhere between 2 to 10%, with the top speed ceiling at roughly 20% the speed of light, double that of the Orion drive. The setback for this is it's definitely very technologically advanced, whether it be the propulsion itself or the shielding from the radiation and heat generated by the propulsion, but definitely worth pursuing. So out of the aforementioned options, I believe that ICF with deuterium helium-3 fusion is the direction we should move in, as we have already achieved a net positive energy in deuterium tritium fusion, and this is a logical next step with much more room for evolution. The direction of progress also has the added benefit of providing large amounts of clean renewable energy, and therefore we should begin focusing research on this and nurturing the seedling, providing shade for generations to come. Thank you.